Problem 97. Find the dimensions of the can whose volume is 350 cubic centimeters and whose cost is minimum. First, let's analyze the constraint equation. That is the function whose value is fixed. The volume of a cylinder is given by pi r squared h, and the volume is equal to 350, so this gives us our constraint equation, pi r squared h equals 350. And we may as well go ahead and solve this for whichever variable is easier. In this case, that would be h. This gives us h equals 350 over pi r squared. So we've done just about all we can with the constraint equation. Now let's move on to the objective equation, the cost. So I know that the cost of this can will be the cost of the side plus the cost of the bottom plus the cost of the top. And we'll analyze each of these separately. The cost of the side will be the area of the side of the can times 0.02. That's the cost per unit area. Now the area of a cylinder is given by 2 pi rh. We multiply this by 0.02. So this says that the cost of the side of the can is 0.04 pi rh. We look at the cost of the bottom of the can, and this is the area of the bottom times 0.03. The bottom is a circle, so its area is pi r squared times 0.03. So that says that the cost of the bottom is 0.03 pi r squared. The cost of the top of the can is the area of the top times the cost per unit area, 0.04. The area of the top is the same as that of the bottom. So this gives us pi r squared times 0.04. Multiplying these out, we've got 0.04 pi r squared. This says that the total cost of the can is just the sum of these three values. So this is 0.04 pi rh plus 0.07 pi r squared. And this is the function that we want to minimize, subject to the constraint that h must be equal to 350 over pi r squared. Let's take this value for h and plug it in to the working equation we have so far. This says that the cost is 0.04 pi r h, and h is 350 over pi r squared, plus, now the second term has no h's, so there's nothing to substitute in here. We'll just copy that down, 0.07 pi r squared. And we can simplify this because we can cancel the pi's, we can cancel an r, multiply these together. So this says that our cost is 14 over r plus 0.07 pi r squared. And we want this to be minimum. Since we're trying to minimize this function, we'll take its derivative and set it equal to 0 to find our critical numbers. So our derivative is negative 14 over r squared plus 0.14 pi r. And we're going to set this equal to 0 and solve for r. So first I'll move this negative term to the other side of the equation. So we've got 0.14 pi r equals 14 over r squared. Now let's move all the r's to the same side of the equation. So we've got r cubed equals 100 over pi. Now we take the cube root to get r equals the cube root of 100 over pi. And this turns out to be approximately 3.169. Now given that this is our r value, we were asked to find the dimensions. So we've also got to find the height. We get this by taking this r value and plugging it back into our constraint equation. This tells us that r is approximately 11.092 centimeters. But now we need to make sure that this actually is a minimum cost. Is it a minimum or is it a maximum? Have we done the worst we can? Well, to do this, I want to know if this is a max or a min. I'll use the second derivative test. So to do that, we take the second derivative. So we take a derivative here. This gives us negative 28 over r cubed plus 0.14 pi. And we're going to evaluate this at our critical number. So c double prime of 3.169. We plug this into our second derivative. This gives us a value that's approximately positive 1.0 319. This is positive, so that tells us that the function is concave up, so that we actually have a minimum. So the dimensions that minimize the cost of the can are a radius of 3.169 centimeters and a height of 11.092 centimeters.